We start our session today. I think along the semesters, some people are changing from morning person to afternoon person. So that's my impression. Yeah. So let's. Okay. So first, how did the exercise session, went last Tuesday? Went fine. Yeah. Okay. That's just to practice. I think I showed you and I made the sketches myself. But I think you have to. I just wanted you very early to make the sketches yourself because that's when you really check if you understood what I presented here in class or not. And at the same time, it's going to be part of your exercise set. So I think that saves some time later. And you can do it by hand, no problem. But I really encourage you if you are going to, it's a nice asset to know how to make the sketches in a program. Hey, you can use PowerPoint, you can use Paint, whatever you prefer, but at least to have it digital, that's really. Initially, it takes more time than make it by hand, but then to have it, the skill is an asset, and you get better with time. Okay, so let's. What we were discussing last class, or the last topic that we stuck with, was offshore structures for oil and gas production. So first, I just said what are the functionality, what usually the offshore structure has, and it doesn't have to have all of these things, but that's kind of all the things that it could have. Right? And we are classifying further them in two categories: one bottom supported, and another one that is floating. And you have different variations within them that have to do first how much movement they have, and also what kind of flotation, if they are positive or if they are neutrally buoyant. Then we saw something interesting. How do you select the structure really depends on many factors. Okay, but one of them very important is which kind of wells are you going to use, subsea or platform. Okay, what we call dry Christmas tree or wet Christmas tree. And in a way, the preference or the selection comes given by just the spread, the physics, okay, the spread of the reservoir. If you have a reservoir that is very spread and you want to drill everything from one location, then your drilling package will be just too big, okay, and it will be very costly. So in that case, you prefer to go for a subsea development and tie back to. So what were the structures that could allow dry Christmas tree, if you remember? First, we have the ones that are fixed, that are jacket, gravity-based structure, and compliant tower. This one they accept because they are just fixed to the seabed. But then on the floating, we had surprisingly two of them. It was the TLP and the spar. If you remember, the spar was that long one. I have a picture of the spar, maybe before. Okay, the spar looks like that. That just all the area, all the hole that it has below the water surface, it allows it to stabilize somehow, and it restricts a bit the movement in all directions. Okay, semi-sub, they're used usually for the subsea wells and also FPSOs. And yeah, I think that's pretty much what we had. Okay, so the selection is very extremely important, which kind of wells I'm going to use. Then the depth, there is a big overlap between the concepts with respect to depth, but if you want to go to something very deep, you usually use FPSO or semi-sub, and if you want to go to something relatively shallow, it's usually more cost effective to use jacket. But anything in between, it's a bit difficult. Then another thing we discussed was the soil characteristics. I told you very briefly. If you can anchor, and you are not expecting any subsidence of the seabed. Okay, if you're expecting any movement, then you don't want to put a fixed structure. Then how often, that has to do with the intervention on the wells. How often do you expect to make intervention on the wells? If you expect to do it very often, then you want to have a drilling package. Okay, then you want to have a dry Christmas tree. So now today I want to discuss briefly the ocean conditions. Okay, how do we characterize the ocean conditions? Okay, wind, waves, and current. How we characterize them, and why do they affect the selection of the structure? Okay, and this is really cover maybe 4 courses in the marine department. So those of you who have interest and want to learn some more, I recommend taking some course from there. But here I'm going to try to give you just the flavor, their generalities, so you're aware of that and are able to, to establish a meaningful discussion later in your, when you're working in the industry. Okay, so let's see. I call it marine loads. So the topic for today is marine loads with okay. And basically we have, if we make the surface of the sea, okay, we have our offshore structure. We're going to say that is this is representing kind of a semi-sub, but really could be anything. Okay, so we have 3 types of loads, or 3 types of marine loads. One of them is wind. Okay, and the wind, we describe it usually, you have a lower velocity close to the sea surface, okay, and then it's increasing, and then it becomes, maybe pull it down, okay, becomes kind of stable. Okay, then we have, so that's wind. Okay, masses of air moving and impacting against the part of the structure that is dry, okay, that is above the sea level. That's, let me pull it sea level. Okay, and let me put the seabed. Okay, then you have on the sea, on the inside the water sheet, or inside the water layer, you have what we call marine currents. Okay, again, movements, displacements of masses of and that usually, I'm going to make it a bit simplified, but it will be maybe something like this. Okay, so that's what we call current. And you get the impression, if the area exposed of the structure is big below the surface, then the current might be important. And then we have the last load, which is the one that we pay most attention, which is, I'm going to maybe put it, maybe I can put it here, which are the waves, the movement of the surface that is impacting the structure. Okay, up and down, and we have, I guess you have taken some physics, some course in physics, and you see how these waves, you have rolling waves, you have stationary waves, you have a mixture of these waves, but basically waves changes in the surface, the location of the surface between the air and the water, and they move on one direction, and they impact the structure. Okay. So one thing to note is that wind and current, they can be described like distribution is like a distribution along the vertical axis. Okay, if you see, this is, if we say that we put an axis here on the right side, y, we say that the wind is a function usually of y, and the current is also a function of y. We don't do the same usually for waves. Okay. But okay, and also something interesting, if you see it from the top, okay, if you see the structure from the top, we put it in the center, so that's top view. you will have usually some particular directions that where this wind, current, or waves come from. Okay, so you have, for example, if this is north, you have south, west, and east. Okay, you have kind of a circle. You might say that the loads, there are some loads, and we are going to, let's put just the axis. Okay, and we have, for example, some loads come from the north, from the east, but maybe the majority is coming from, okay, from the southwest. Okay, for that particular case. So keep that in mind. Also, marine loads usually have a preferential direction that we have to take into account, and it might be different for each particular load. Now, for practical considerations, for practical purposes, wind is usually considered constant. What you make is an integration on the surface, and you can say I represent all the wind by one component, and that's constant, that it doesn't change with time. Wind with a uniform value uniform constant value. Okay, that's one exception to that is floating structures. Some floating structures we want to put the transient nature of wind, but let's, not to make it, we say exception, some floating structures. Okay, and current, you usually consider the variation with depth, the variation with the variation, the spatial variation. In current, the spatial variation is considered. But it's also considered constant with time, that it doesn't change with time. And you usually use something that is a value of the current which is very high and is likely to happen in a very long period. You can use 50 years, 60 years, 100 years, but it's the value of the current that you can expect to happen at least once every 100 years. Okay, the 100 years current. A high value is usually used. A 100-year current. And we are going to focus now, so because these simplifications that we used, really it makes it simpler to work with wind and current in a way. But waves is where you have a variability with time. So that we are going to focus on what do we do then to capture wave, the change in waves. But you can apply, if you want to do the same thing for wind, you can also do it using the same tools. But we are going to focus on waves. Let's see. I forgot to say the periods. So let's see. Wind has usually variations of hours. Current is in the range of hours. It changes in the range of hours, so it's very slow changing. while wind usually values vary with the minutes. So just you have an idea how fluctuating are these loads. But current is relatively stable, changes within hours, within days, but wind is more variable. Okay, so now let's focus on the wave. Now let's focus on the wave, which is really what concerns that we use for design, what we have really to capture for design for each particular offshore structure or in one particular area. So let me pull a figure. I think I have a nice figure. Okay, you have here these rows. It's called, in this case, it's a wind rows. Let me just pull it. I think it'll be interesting. Then we put some colors on the notes. Wind rows indicating the direction and where do you expect the highest wind, okay, and for how long. Okay, so let's waves. They look, if you say what I'm doing here, I'm putting a reference. Let me put it on the next page. I'm making a reference that's called wave elevation, and I'm attaching a reference to a constant sea level. Let's say that's the average. I make the average and I fix the sea level, and that's at a particular height from the seabed. So when you say a particular development, Snow White or Gulfax has 400-meter water depth or 400-meter water sheet, that's you're talking about. That's going to change, fluctuate slightly with time, but you're referring to the average depth, to the average height. And we say set T is how the elevation will change with time. And in principle, you see here you have the impacting the offshore structure. So in principle, that looks very erratic and difficult to characterize. You say, how do I characterize that strange behavior? It's like I cannot assign a function, I cannot assign. So anybody knows what we do when we have these kind of signals? Where we cannot recognize, so here we cannot recognize a clear pattern. We cannot recognize a repetition. We cannot recognize, we know that there are some fluctuations, so there has to be some periodicity. How is it called? Periodicity in the signal. There has to be some fluctuation, but how do I detect from this signal, how do I detect this periodicity? Anybody? I guess some of you took these advanced applied numerical methods for petroleum engineering. Yeah. So you didn't see something called a strange French guy called Fourier? Remember sounds, no? Fourier? You didn't cover it in this course?
Fourier transformation.
Fourier transformation. So what Fourier said, if you go back, try to undust that part of the brain that has the information. So what Fourier told us? Fourier, as I remember, you have to correct me also, but Fourier told us that if you have a very complicated signal, it doesn't matter which kind of function, which kind of signal you have, if it's continuous, you can represent it as a sum of sinus, sine and cosine of different frequencies. Is that correct? That rings a bell? Let me just put a figure. Okay. That was what this great guy, mathematician, okay, he said if you have a very strange signal, okay, very complicated, at the end you can say that signal is going to be the sum of many different signals, each one with its own amplitude and its own frequency. The thing is that if the signal is more and more complex, it looks more and more random, then you have to take more and more components. You have to take, for example, here the period is relatively long, here the period is shorter, so you have the range of the period, you have to make it broader. That you saw that someplace before, I hope. No? Okay, that's called Fourier theorem. Well, of course, if you go to Wikipedia, you will have maybe a hard time. It's not the okay, that's the guy. Yeah, and it might be a bit heavy to understand, but it's basically what I told you here. You try to decompose a very complicated signals in something that we know. Okay, that's a guy. So the way we do that, so to calculate, you say, okay, that's very nice, but how do I know which components form that signal? Do I do it by trial and error? So we have a procedure that I'm not going to cover here that is called FFT. It's called Fast Fourier Transform. And it's a way to do very efficiently to compute each component, each frequency component, and to compute the amplitude of each one of these components. So at the end you obtain for a given signal, if you apply fast Fourier transform, if we apply the fast Fourier transform to a signal, okay, to a wave measurement, for example, you have done some measurements of wave. By the way, how do we do these measurements? Okay, we're going to come to that later, but or maybe I can just say now. Okay, wave measurements of wave statistics. They're usually done by buoys that you allow them to float and go up and down, just follow the sea level. You can also use them attached to vessels, so vessels go and they measure. You can also be from lighthouses that they measure just close to the shore, how is the variation of the sea. There are many different ways. Let's see if I'm missing something. Okay, measurement of wave statistics. So it's done usually buoys. So that's a difficult word. How do you write buoys? It's U-O-U buoys. Okay, attached to ships that are making delivery across continents, for example, to merchant ships, to measurement ships. Okay, if you have already an offshore structure in the area, you can just attach it to the offshore structure, to existing offshore structures. And of course you want to have measurement for as long as possible. If you are going to go to a new area, for example this Osta Hanstein that I mentioned last class, so you have to have information for enough time on the area of how the wave statistics are, and that depends, sometimes is limited. You don't actually, maybe you didn't measure exactly on that place. So that's one thing that we are going to see, how to extrapolate wave data. Okay, but going back to our guy, so if you apply you measure some data for a certain period of time, and then you apply this fast Fourier transform. And Excel, maybe we could try to make an exercise here in class, but Excel it cannot handle a huge amount of data. It's limited with the number of data that you can use. It can do fast Fourier transform. It's better to use MATLAB. It's quicker and it doesn't have any limitation. But then we have a problem if you have MATLAB on your computer. So I will think a bit about it and try to find a solution. But if you apply FFT, you're going to obtain at the end a graph that is called, what, don't want to mess up the name, wave energy spectrum. That tells you on the y-axis you have the frequency, and that frequency we usually use the letter omega, and that frequency it's in per second. And we have here what we call the spectrum, spectral energy. Okay, and we, in this particular case, we use the letter S of the variable. Okay, that is this the elevation. We use this strange variable called. So I have to make some practice. Okay. So the spectral energy of that particular variable, and that has units of square meter per second. So you are asking why that guy appeared here. What is that spectral energy? We had our signal. You're just standing too quiet. Yeah, the detector thing should be here. So you're saying we have is elevation data. So why this spectral energy came? And that's just part of the calculation that you have to. Fourier is basically it's something that is that from the calculation it appear that spectral energy, but you can convert later on from spectral energy to elevation. I will show you. I will give you the formula, but this is basically an indicator of that particular coefficient that goes in front of the sine or the cosine. Yeah, and you will obtain something like this. Okay, and maybe 0 for the rest. So that tells you exactly each one of them, these components, is that sine and that frequency associated. So you have one frequency associated and the amplitude associated. And that is a way to describe your signal. To describe that very complicated signal that you think it doesn't have any trend, doesn't have any, it's not cyclic, then I can describe exactly that wave by this particular spectrum. Okay. And some formulas that are typically used for the spectrum. If you want just that you will get familiar with the name, it's called Pearson-Moscovich. Okay, it's sometimes abbreviated as PM, or also John Swap. So you measure data in certain, and now we are going to talk about time scale. So when is this data measured? We already agreed that it would be nice to have a very long period of time, but due to the changes, we cannot use one period of time, and we're going to see that right away. But if you measure for a certain period of time, you get measurements, and then you can tune and use one of these particular distributions. They say these distributions usually represent very well the wave behavior. Okay. So let's now make a distinction. So for what we call short period of time, that is called a C state, okay, for short periods of time, and that's what we are going to call a C state. And usually, so people historically, they have seen a C state lasts for approximately between 2 and 3 hours, and there are different variations, but in the oil industry we use 3 hours. So two things happen in those 3 hours. First, there is a significant period or we also call it the mean period, which is dominant. That will be, if we see that plot, that we have one very clear peak, frequency peak, that we say that's TS. Well, you have to convert from frequency to period, but that will be my dominant, my mean period. And I can characterize really in these 3 hours that I can represent most of the waves with that T. But that's only if I look at 3 hours. Okay. There is a significant period and is usually considered constant. So we can approximate, if it's really short, 3 hours, one sea state, that you have one, you can just report one frequency, and that's enough to characterize the whole 3 hours. But now the wave elevation, on the other hand, elevation, it displays what we discussed the other day, the Gaussian distribution. Okay, it just displays a very nice normal distribution. So you have the wave elevation, which was this strange letter in meters, and if we calculate the probability density function, it's just going to be a normal distribution. Okay, so you have some variation of the wave in this 3 hours period. But now let's change. So we are not really, I lied to you a bit. When I talked here about wave elevation, that's not really what we are concerned of. Usually what we are concerned is the wave height, which is the difference of two consecutive waves. That will be the wave elevation, and we are going to call it with the letter H. And that's what we use usually for design. The two things are kind of equivalent, but we want to get is the highest, is like the highest water height that is going to impact the offshore structure to calculate all the loads. So that we call height, and is the difference between two consecutive waves. Okay. And the wave, the height, the wave height, it doesn't display this normal very nice distribution, but it displays, so that will be 0. Remember, in the PDF we have at the x-axis we have the variable, and on the y-axis we have the probability. Okay. But the wave height looks like a log normal, what we already discussed, a log normal distribution. So PDF of the wave height of H, if that one looks normal, then that one usually looks like a log normal distribution, or we also call it, just that you don't have to learn the names really, but you just that it doesn't sound strange when you see it someplace, is Rayleigh distribution. And that Rayleigh distribution has one H that we call the mean height. Okay, or what we call the sorry, that's not the mean height, that's fine, but what we are going to use is don't want to complicate, but so you have one value which is H max, and you calculate h max divided by 3, and you take the average of h in that region, and that's significant wave height. Okay, don't want to complicate, but you take the maximum height, wave height, you take 1/3 of that, then you define a range, and then you integrate on that area, and you find the average wave height, and that's what we call the significant height. We're trying, just not to confuse you, we're trying to, in that period, that very complicated wave, we're trying to get two indicators. Okay, remember we need two things. We need something indicating the frequency, and you see already how we have done it. Take fast Fourier transform and get the peak. Very simple. But we also want to get some indication of amplitude, indication of height. So we said all the variations in elevation, they follow this Gaussian distribution. All the variations of height follow this Rayleigh distribution. And now I calculate a number from this distribution that is representing this particular state. And that number is this HAs that I told you. Okay? So don't be confused how we calculate it. It's just we want to get two numbers, frequency and height. Okay, so that's what we call significant wave height. And with these two numbers, TS, so actually we have TS, okay, and HS characterize a C state. Yes? So if someone says for these 3 hours, which waves do I have to consider? So you give them only those two numbers, and the guy knows that the height will change following a Rayleigh distribution, and they can generate very quickly, and the frequency will have this Jones-Vapp shape, exactly the Jones-Vapp shape, and they can use those two equations only with those two numbers to reproduce the wave state in that particular 3 hours. Okay. However, for long periods of time, there will be many C states. Okay, there will be many of these 3 hours period, and each one of them might have a different significant period and a different significant height, which is something natural, okay, normal that you will expect. So don't be scared. The information is usually presented like that. Let me put it here. So that's what we call a scatter diagram. Let's put the name so you're also getting used to it. Scatter diagram of long-term wave statistics. And in this particular case, that's for that field, Osta, Hanstein, in mid Norway. So what you see here, if you see at the top TS, okay, or they call it spectral peak period, that's where you have the peak, and HS, okay, on the vertical axis, tells you the significant wave height. So you have a collection. First you have a range. Okay, so what we really measured was one state, for example. If you get one TS and one height, you put it here. Okay, so that's one state. Then you go and measure other 3 seconds, and for example, fall here, you put 1 here. Then you measure other 3 hours, and you put it here. So at the end, you collect data for 15, for example, in this case, it's for 15 years. And you will see that there are some regions that they occur more frequently, that some combinations of TS and HS that occur more frequently than others. Okay? So this is a collection of all of these 3 hours. So each number here, 1, is only that combination of 19 to 20 seconds change, okay, with a 15 meters wave occurred only once in this 15-year period, measurement period. Okay? Remember, 1 represents 3 hours. We are assuming that the sea is constant in these 3 hours. Yes? That clear? More or less? Okay. So I'm not going to talk about so usually that data was measured for 15 years. And I usually want to extrapolate that data for 100 years. We need, sometimes for some design conditions, we need the 100-year. We are almost closing to the break. Just give me 5 minutes. We need the, not in 15 years, but we need in 100 years period. So we need to make some extrapolation on this data. So to get, so let's put that like that. Design is usually made using values for longer periods. More usually that one is measured. You usually can measure, let's say 20, 15 years. If you're lucky, maybe 50 years. But if you usually want to make your design at least to be very conservative for at least 100 years, and you don't have measurements for longer periods. So you need to perform an extrapolation. And we are not going to talk about it, but just that you're aware that you need to extrapolate this data that you measure. That we need to extrapolate that data that we measure. Okay, but I'm not going to, I don't want to complicate it even further. Okay, so that's how we characterize that's how we characterize the wave. Any questions so far? Okay, wind usually constant, doesn't change with time unless we have floating structures. Current, we take the variation with depth, but usually we consider it also constant. We have to take into account the direction where they come from. And waves is more complicated, but you use for 3 hours period Fourier transform to get the peak, the frequency that has the maximum energy. Okay, and then you say that the height, I'm not concerned about the elevation, but basically the height, the difference between two consecutive waves, the highest value and the lowest value. And to characterize, I use a tricky procedure, which is I make the integral of the max and 1/3 of the max. And that's the age that I report has a significant height. And for longer periods, if we want to measure for 15 years, I will have a variation of that particular combination. And I will have, in this case, you see those parts in green, they're really the most frequent. So that C is characterized by period between 9 and 10 seconds, which is relatively quick, and 2 and 3 meter wave height. Yep, you can have actually bigger waves of 15 meters, okay? Very scary. But they are not so frequent, at least in that 15-year period. They occurred only once. Yep. And the last thing is that data was gathered for a limited period of time. We usually need for a longer period, so we need to extrapolate based on that data. And that, well, yeah, I'm not going to cover in class. Correct? Yeah. So let's take a break and we come back to see how we use that information to design our structures. Okay, we continue our discussion. I think, I will risk to talk about the extrapolation, okay, if you allow it. I think it's important just that you get a feeling how that extrapolation is done. So if you see for each one of these periods, okay, you have different wave heights, right? Okay, for the 16 between 17, you have all of them, and that will give you actually a PDF. Okay, if you, for example, let's say looking at a TP with the spectral peak period or the mean period, spectral, and you know now where the name spectral came from. Okay, it's the highest peak in this fast Fourier transform plot. Spectral period, peak period. And you see at the height, it will look, you can make actually a PDF that's going to look okay. In that case, let's see, we look at that particular case of 15 to 16. It will go very quickly. The most frequent wave height is between 2 and 3, and then it will start reducing until it reaches 1. Okay, very simple. So each one of them, if you cut it, slice it one particular column, it will have that one particular distribution. With that particular distribution, you can calculate, if you make the cumulative distribution of height, so that's wave height, okay, and you make the cumulative distribution, you get maybe something like this, 100%. So the a 15-year wave, okay, the H significant 15-year wave for that particular period range, okay, we are now looking at each particular period range. It's going to be that at least occurs once in a 15-year period. Yeah? So 15 years is equivalent to, and you can make the calculation to verify, but I hope I'm correct. Have it here someplace. Okay, is equivalent to 292,000 states of 3 hours. So the wave, the 15-year wave, is that one that occurs only once, at least once in that period. Okay, so therefore it has a probability, has an associated probability of 1/292,000. Okay, and that's something like, something very, very small, 7.6 e to the 6, e to the minus 6. Okay, so if you want to know what is for that particular TP, okay, for this particular TP, what is the 15 years wave, you just come and you put that value here. That plot, I think usually it's plotted the other way. Okay, like that. And you go and check exactly which wave height I got for that probability. That will be practically 0. Okay, will be almost very close to 0, and that will be my 15 years wave. Now, all the waves in all of these years, 15 years, in all of these periods, 15, 50, 100, they follow, we assume that the significant wave height in different time periods follow a logarithmic distribution, okay, logarithmic equation. and you have the probability the log base 10 of the probability of h is equal to 1 over a times h. It follows that relationship. So if you have for 15 years, you substitute 7 point, how much was it? 7.6 e to the minus 6 log of that equal to 1 over a h 15 that you read from the plot, you can get a. And then from that point, you can extrapolate how many just changing the probability. Okay, if you have, for example, 30 years, you have 2 times that, so it will be that probability divided by 2. Okay, so you can find what will be the significant wave height in another year's period, 50 years, 100 years, etc. So that's how you extrapolate based on a very limited 15 years period, how you extrapolate for 100 years. And 100 years is a data that we want to have for design purposes. And please note that you can make the same for different spectral periods. Okay, we have done that now between 17 and 18, but you can repeat 18 and 19 and so forth. So you can really extrapolate for other periods. Okay, so now let's see. Okay, you explain quite detailed, you know, how we make the statistics. So how do we use the statistics for design? That's really what we are concerned. So calculation of forces, okay, or displacements, we can say, of offshore structures. So just before we say anything else, we can say usually bottom fixed structures, okay, like GBS, they usually they deflect if you have 0, no displacement at the base, and you have certain displacement for every y position. Okay, y has a function of time, so it will tend to move like if it was a bar that is just anchored in position at the seabed. Okay, and it's going to move, and it will have certain deflection due to the variation of properties along the structure. So that's how bottom supported structures move like. And floating structures, if we see a boat, okay, and let's see if I attempt to make a boat, it will have movement up and down, which is called heave. Okay, we'll have, remember, the boat can move on that direction, can move on this direction, can move on this direction, can move, what else can it do? On that direction, okay? It can move really in so that's called heave, if we have it in the vertical movement. Then we can move on that direction, that is called yaw. Then if it moves on that direction, that is called surge. So we can put an axis through it, and just that's called surge. No, that's called roll, sorry. And movement on that direction is called surge, forward and backwards. Then we have sway, which is if we displace in the lateral direction, that's called sway. And we also have rotation in that direction, which is called pitch. Okay, very complicated. Okay, we can move actually in any direction. But usually there are some directions that are more, for example, heave is extremely important because of the load on the risers. Okay, when they move up and down, the risers will also experience some expansion and compression. So the heave is extremely important. And if you have, for example, a spar, okay, remember the spar looks something like that, and the pipes, they go inside the spar. So the movement in that case, the pitch, when we move on that direction, if we move like that, it will cause some stresses on that particular piece of pipe that is leaving the spar. Okay, because that part moves differently than the part that is inside the spar. So it can cause some fatigue in those pipes that are leaving the spar on that part. So really the loads there are different loads that are important for each particular case. But usually it's heave, and we have pitch in spars, and for for bottom supported structures we have deflection similar to a bar. Okay. So the significant wave height in 100 years is used to determine what is the height that you have to have between the sea level and the deck. Because if you see I have a wave, I don't want at any moment water to come up into the deck, because then it can damage the wave, can damage everything that is on top. So it's used to design deck height. That's one use of the HS. And then what we use, all of these loads, all of these marine loads, current, wind, and so the more or less the workflow is wave, wind, and current. They are used to calculate. So that's, and you have here the statistic description. And then you calculate forces on the structure. It's like, for example, currents. If like the case we were discussing last time, you have a current impacting the bottom part of a spar, you can calculate certain force acting on the spar, okay, certain displacement that is pushing the spar on the side, and that will change with height. The wind, a similar behavior. The waves, it's like impact loads on the structure. So you calculate forces on the structure, and you then calculate displacements on the structure. Okay? And then you verify displacement and also stresses in the structure. You want to be sure all the time that the stresses do not go over the resistance of the material. And you calculate stresses on the structure. Okay, and we are not going to go into detail on that, but there are one thing that I want to mention. So we make three types of analyses are made. Three types of analyses are usually made. One is using a design wave, where you use the HS100. Okay? You're assuming that the structure will experience a storm of at least that particular magnitude, and you will use, the periods used are usually HS with a range of periods. Okay, so you will apply that particular wave height, apply some particular period, calculate forces, and see how the displacements are and the stresses are. And with a range of periods, and just that you have it like a reference, the NURSOC, Norwegian Standard, I'm not sure the OK stands for, is the equivalent to the API in Norway, NURSOC N003 suggest using square root of 6.5 HS 100 and square root of 11 HS 100. Okay, using a t within that range. If you have that value, then you can see, okay, we'll use the period will change. I will make analysis varying the period. And if you don't have the HS, you don't have more sophisticated statistics, then what you can use is that HS 100 is equal to 1.9 HS, the significant wave height. You don't do that extrapolation if you don't have enough data. You just take the measured height and multiply it times 1.9. Then you have a a short-term design. And that's usually done with a particular combination of HS and TS. Okay, and that's done usually to calculate maximum loads and stresses on components. Okay, you want to see if the structure for a particular sea state it will withstand that particular. It's almost like a storm. Okay. And then we have another type of design, which is long-term design. Where I try to take a longer period of time, for example years, and then I try to see if there is any component that will be prone to fatigue, for example. Fatigue, remember, is not something that we usually have in a very short period, but it's something that accumulates along the years. So that's why we use this long-term design. Varying HS and TS, okay, it assumes some variation of HS and TS, and is used to calculate fatigue, basically fatigue resistance. Okay. So I don't want to go too much into detail, but those are the three main things. You make a design wave and you change slightly the period. Then you make a short term, you're focusing on one particular sea state, it's very aggressive conditions if the structure will hold, and then you make a long term design where you have some variations. But please take into account that if you have a change in time, here you will also have an answer that is changing in time. So you also have to apply statistics on the response. Okay, and that can be tricky to determine how the loads are changing with time. So you have to really use stochastic or statistic treatment both for the loads and both for the results. And you have to have a model in between that is able to convert between one and the other. Okay, and if we include more forces, if we include more variations, this becomes very, very, very heavy to run, very complex. So we want to find a right balance between simplicity and something that really captures the behavior. Okay, and just to finalize this part, each offshore structure has a value called natural frequency. Anybody familiar with natural frequency? No? Have you heard the term before? Natural frequency? Yeah. What is it? Okay. If I, for example, take a bar, okay, that is suspended like this, and it has certain flexibility, I just make one I just push it once, and then starts to vibrate. It will vibrate with certain associated frequency, and that frequency depends on the weight of the bar. It depends on the elasticity of the bar, and it depends on the losses, the energy losses inside the bar, and that's what we call the natural frequency. Okay. And simply, so each mechanical structure has that value. Okay, even if it's not the bar, but it's a huge structure, it's a huge part that is made of different things, and really you don't imagine how do I put my finger and touch it, okay, but they have some natural frequency that characterizes the structure. And depends, so let's write that, each offshore structure One question. I'm writing, trying to write as much as possible in class, but then it takes time, and I kind of cut the discussion. Do you want me to continue like that, or you prefer that I would talk more and write less?
Right.
Write more? Yeah. Okay. Everybody agrees? Write more? Yes? Okay. Each offshore structure has a natural frequency. Okay. The natural frequency, if I excite with certain load and then with one impulse load, for example, and I leave it moving alone, is going to exhibit that frequency. And for complicated structures, you really have in each direction, you have a frequency, a natural frequency. Let's say for floating structures, you have one for heave. If you have a bottom supported structure, you have one for deflection, etc. And they depend on the flexibility of the structure. They depend also on the weight of the structure. And on the damping of the structure. I'm not sure if you have anyone here from mechanics, but you have a system, and usually any mechanical system you can represent by a mass, by a spring, and by a damper. Okay, so that's C, that's K, and that's mass. And you can represent basically in a simplified way any mechanical system with these three characteristics. And they define the natural frequency. And you don't want that the excitation, okay, so to make it simple, you have a phenomenon that is called resonance. That the resonance, it's when you excite the structure exactly at the frequency or very close to the natural frequency, you're going to get the highest amplitude possible. Okay, I move the bar, and I see the frequency, and then I excite it exactly with that frequency. If I do it exactly like that, my amplitudes will be very, very high. And if my amplitudes are very, very high, the loads and the stresses are also high, usually high. That clear? That's what we call resonance. We excite, so let's put it here, resonance. Excite. Okay. This structure with the natural frequency. Okay, with a load that has exactly the same natural frequency. And then the amplitudes will be big, okay? And if amplitudes are big, then stresses and loads are usually also big. So we want to avoid any load. If you detect certain structure has certain natural frequency, you want to avoid that so you cannot use it for that's something that is given by nature. You measure in one area that they have certain characteristics, so you cannot put in that area a structure that has a natural frequency equal to the excitation frequency, because then it might be destroyed very quickly. So let's put a plot. Put it a bit smaller. Okay. And the period also changes with water depth. So here you have the natural period, this natural frequency, okay, and you have all the different structures. And you see that Jacobs, they have some variation when you make it longer, okay. You also are changing the characteristics. You're changing the elasticity and you're changing the weight. So they will have some change, but their natural frequencies will be someplace around here. Okay. Then you have the jacket, then you have the tension leg platform, and you see is the displacement in one, you heave, okay, roll, and pitch. the natural frequency of these three things. And there are some things that are floating, for example, the semi-sub, that they really don't depend on height, okay? Because they are not bottom supported in any way. So, but their natural frequency for heave at least is on that range. Okay? And now that's on this side. And so you have spar, TLP, all different things, and with their frequency. Okay, but then you have on the left side you have the loads and what is the range of frequencies that they cover. Okay, you have wind, for example. Okay, wind is usually up there, so it will affect very much floating structures. Okay. You have wave, okay, drift. You have different phenomena related with wave, but wave, for example, would affect that part. Vortex shedding will affect that part, etc. So if you characterize your loads, and you're expecting loads very strong within certain range, there are some offshore structures that you shouldn't use. Yes? Okay, because you don't want that the natural frequency will be the same as the excitation frequency. That's what you cause resonance, you cause high displacements, very high loads, and then you can damage the structure. Okay. So that's just to summarize the discussion. You usually have to do that procedure, okay, and with different loads, and also doing statistical treatment. But you want to avoid that if this one has a natural frequency, that this one will coincide with that natural frequency. Yeah? Any question? No? Okay, so that closes the discussion on offshore structures. I made some notes and I will publish them. They're not in the compendium, but I will publish them on its learning. So if you want to, something that was not clear, I think you can go through it and read. But basically is the discussion we have had in class. Now let's go to a completely different topic, which is the flow performance of the production system. So why is it important to try to characterize? Also, by production system, I'm referring to, if we make our very simplified system, we have our reservoir, we have our well that we already discussed, all the valves, and we have a pipeline, and at the end, if we have, for example, a platform. So by production system, I'm saying everything from the reservoir, okay, from the reservoir to the separation facilities. This color. Okay, that's my production system. We will see later so that's my production system. And the main thing about that production system, or something that affects my field planning design, is really how much the Q of the field, how is it going to be with time. Okay, that's something that we really want to, if we have our production system, we want to be able to quantify how much that system will be able to produce with time. Because with this one, then we calculate the revenue, and with the revenue, we calculate then the NPV, and then we can decide, okay, did we get a high, low value? Then we can repeat and change. Try to change something in my production system. For example, changes might be increasing the number of wells. I can change the length of the pipeline. I can change the type of the well, and I can try to see what will be the effect on the how much I'm producing, and at the end, lately, on the NPV. So for that, usually, to compute the performance of production systems, we use numerical models. And why numerical? So models first, they are based on equations. They are based on physical principles, and they are supposed to capture the most important phenomena that is happening in every part of the system. Okay, the flow in porous media, the phase behavior, the flow in pipes, the multi-phase flow in pipes, the multi-phase flow in pipes, and the pressure drop from the well, for example, to the separator is expected to capture all of that complexity. And then one thing, if we have a numerical model, that can be like, I have now like a virtual representation of my system, and I can make any variation in that system as I want, and then the idea is try to find the best way to operate that system, or the best configuration of that system, and apply that in the real asset. Okay? I want to find the best way to get the most out of that system, and then after I have a final solution, I can apply those things that I learned in my real system. Remember, the real system, I can produce it only once. The virtual system, I can produce as many times as I want, with as many variations, and try to see what is the optimal way to manage it. Okay, so let's as I told you, there are different approaches to capture the performance, so at least to start calculating the performance of production systems. So one of these approaches is, as I told you, okay, I think we had that discussion some time before, that you have two phenomena. If we see our production system as a tank, we have two phenomena. One of them is that we are taking material out of the reservoir with time, so the pressure is going down with time. And remember that I told you that somehow, if we make our analog, and here we have our separator, the rate that I can produce from that system is somehow proportional to the difference in pressure between reservoir and separator. Is somehow proportional. So if I reduce the pressure in one of the bounds, if I reduce the pressure at the reservoir, I can produce less. I will produce less and less. So that's the time. So one part of the model is really to capture how the pressure in the reservoir is reducing with time, with production. Okay, the behavior of PR with production. Then another thing is to calculate the rate, and that has to do with all the pressure drop that I have along the system from the reservoir all the way to the separator. So you have, that's the time effect, okay, and that's the rate effect. And you need to have, if you want to predict rates, you need to have the two elements in your model, the two things. You need to have the time effect, the transient effect, and you need to have the pressure drop effect, these two things. And that's usually done at an early phase, because the problem is sometimes we don't have any idea, or there might be many options that I can use for the surface. Okay, many options, but the reservoir is less uncertain. I mean, I have the resources that I have certain information. So one approach that is very typically used early in the design phase is just to use reservoir simulation and ignore in a way all the rest of the system, all the well bores, all the flow lines, and all the separator. So in early phases of field development, and the surface production system and the surface production system is ignored. And reservoir simulator has those two components. Okay, reservoir simulator has how the pressure is going to change, and then due to Darcy law, it has a way to calculate how the fluid is going to flow from one cell to the other. So reservoir simulator has enough equations to compute that behavior. So how many of you have worked with reservoir simulator? None of you? 1, 2, 3. So we don't have enough time. There is a full course for that, but I think it's important for this course that you understand what kind of input and what do we get from the reservoir simulator. So we are going to use a proxy reservoir simulator, and it will be the same way, but we will do it using material balance and IPR. Okay. Basically, if we look at the reservoir simulator, let's put the grid. Okay, first I have to make a map, a grid of the subsurface. Let's see, for example, that I have that, or let's make it just squared. Okay, let's see, imagine that we have a slab, that we are representing a reservoir if it was just a slab. And we have to discretize to put the change in properties. Each cell here might have different porosity, might have different permeability, might have a different saturation, but I have to populate and I have to provide for each one of the cells. I have to provide the oil saturation, the water saturation, the permeability of that cell, vertical. I have to give permeability in Y, permeability in X, and permeability in Z. Z, X, and Y. I think it's the opposite, X and Y. What else do I have to provide for each cell? Porosity, capillary pressure. Okay, it's a bunch of input, and usually sometimes you wonder, so initially you can make it very uniform, but then if you get more information from appraisal wells, you get more information from seismic, you try to refine it and make some variation of properties along the reservoir. Okay, but the thing that you have to, and also I provide initial reservoir pressure, PR initial reservoir pressure. I provide also the fluid properties, that actually it's something that tells me the properties of the fluid, that is viscosity, density, some other things that I might need as a function of pressure and temperature. Remember Darcy law? Anybody remembers how Darcy law looks like? K, dP, dr, K over me. Yeah? And yeah. Is that correct? Yes? So I need the properties of the fluid to calculate the rates. So that's why I need to have properties in every point in the box. Now after you provide all of that, you have to provide also the location of the wells and the number of wells. For example, you have one well here, one well here, one well here, and one well here. Okay. So we will say that the only boundary conditions of that model, if we talk it mathematically, are going to be really the wells. the well cell. For example, it might be just that cell is where the well is perforated, and there I have to provide some condition that tell me how that well is going to produce. And I think we have discussed that before, but we provide two things. One of them is the well rate that we call the target rate. That's the rate that I want to produce if possible. And then next to that, I always provide the PWF min. That's the minimum flowing bottom hole pressure. That's supposed to represent from that point. Remember, now we are standing here. That's the interface. What we are discussing now is only that part. But that pressure is supposed to represent the minimum pressure that you have to have in that point to flow all the way to the surface. So that's really a very critical number, and it's something that is not easy to calculate. Okay, but it's supposed to represent, if you have at least that pressure, you will be able to flow through the whole system all the way to the separator. You are physically able to flow. Okay, so you get these two numbers. And then you perform simulations with time, and for each time you make certain operations, and you calculate rates, and you calculate pressures in each one of the well cells. Okay, so you obtain the result of the reservoir simulator is PWF of each well, of well I, with time, and Q of well with time. Okay, and it will use, so we are going to make now an example. We are not going to use a reservoir simulator, but we are going to use a proxy, like some estimate of reservoir simulators, so you see exactly how it works. But it's basically the same principle. And we are going to use it to predict production profiles. Let's say we're going to work now on the Snow White field. That is a field in the Barents Sea, just offshore, maybe 160 kilometers from a city called Hammerfest, North Norway. And we are going to try to estimate, using a reservoir simulator proxy, the production profile. So I'm going to upload now an Excel file on my website. So if you want to follow with me what I'm doing, I recommend you taking your computer and following in Excel, okay, downloading it. But let's take now 15 minutes break, and we come back for the last part. Yes, so we are going to Snowbit field. Okay, Snow White field offshore. That's in the upper part, the northern part of Norway. You see maybe the distance from Snøhvit to Hammerfest, 160 kilometers. So let's say we have done some pre-analysis. We have seen more or less what are the reserves in place, and now we want to compute. We want to compute how much we can produce with time, the production profiles of that field. And for that, we don't have reservoir simulator, but we are going to use a surrogate that I hope will illustrate how the calculation is performed. Okay? And first, the approximations we are going to make is a dry gas, so it's purely gas that I have in the reservoir. That's not entirely 100% true. You usually have some condensation, some heavy components drop off the gas when you cool it, but we are going to neglect them for now. And the surrogate, the proxy that we are going to use, we're going to use two things: material balance, okay, that will give us how the pressure is going to decline with time, depending on the amounts of gas that I'm taking out of the reservoir. And then for the productivity of the wells, I'm going to use something called IPR, inflow performance relationship. Anybody? I guess you have heard from IPR before. Who hasn't heard about IPR before? All of you? Okay, great. That makes it much simpler. So IPR, if you remember, IPR, it's a curve, okay, that it tells you which rate, that rate, remember, is at standard conditions, which rate you will obtain from the formation if you apply certain flowing bottom hole pressure. If you apply certain pressure, okay, here, exactly here, what will be the rate that you are going to get? And for gas, it looks something like that. What happens when you don't have any flow? Which pressure should you get in the IPR? Just reservoir pressure, right? At that particular time. But now what happens with time with the IPR? That point is going to go down and down and down. So the IPR usually looks like that. Okay? A family of curve that when reservoir pressure is going down and down, every time I'm able to produce less and less. Yes? That's with declining reservoir pressure. And we are going to use one particular expression for the gas IPR that is called the back pressure equation. That the equation is Q of gas is equal to C of the reservoir, the back pressure coefficient, times PR squared minus PWF squared to the power of n. Yes? So that's the expression we are going to use, and yeah, we will, and the material balance that we are going to use is the dry gas material balance, that is PR equal to ZR over ZI initial. Z is the compressibility factor, the deviation factor, times PI times 1 minus GP over G. If you remember, G is initial gas in place. GP is the integral from 0 to time t of the Q gas in dt. Okay? And the pressure, initial reservoir pressure, so that's initial pressure. Then I have the initial deviation factor, and that's the current deviation factor at current P, at current PR, reservoir pressure. So how do I use that equation? Okay, that equation is exactly what we were looking for. Something that tells me how the pressure is going to go down depending on how much I'm taking out of it. Okay, and usually this is called the recovery factor. Okay, for that particular PR. How much I have taken out, that we call the recovery factor, and I think we, using SP nomenclature, we can use RF because we want to have just one capital letter with SP convention. So how do we use that equation? Okay, so I say so I provide, as an input, I provide PI ZI, okay, and I provide also GP, the cumulative production. That's my input, okay, and also G, or these two I can represent by the recovery factor. And then I have, in my equation, I have this term, this term, this term, and this term. But I have these two things that are unknown. And I want to clear the pressure for that particular GP. So how do I do that? If you remember, Z, C, is a function of what? If you remember from the course of Whitson, it's a chart that looks something like that. Okay? Wait, too big. Okay? And I will give you an equation to calculate it. but basically set the compressibility factor, and you need the reduced pressure. What is the reduced pressure? P R over, well, let's call it just P over critical pressure and T over critical temperature, right? So you say which reduced pressure I have, which the pseudo reduced temperature is on top of the line, and then you read what is your deviation factor. Okay, so you say if I have the pressure, the temperature, I have to have it. Okay, something that I need for my calculation. So first I need the critical pressure and temperature, and then I need the pressure. Yes? So to make your life simpler, I have made a function that gives you PC and TC as a function of the specific gravity of the gas. Okay? So to make your life simple. So that's solved. If I have the specific gravity of the gas, then I have it. But now what do I do with pressure? Because that's exactly the same pressure that I have in the equation. So it's, how to say, an implicit equation, right? That I have the variable that I want to clear is somehow here in that part. So the procedure, those of you who took the course of numerical methods, what will be? Remember, if I don't know, I assume. Okay? I assume a pressure has to be lower than initial reservoir pressure, calculate the Z, then substitute in this equation and verify. Is the pressure that I calculate equal to the one that I assumed? No, I repeat the procedure. Okay, until the two of them are the same. Is that clear? Yeah? So that's, let me just put it here, an implicit equation. So I have to assume PR, calculate Z, then calculate PR from material balance, and then I have to check if PR calculated is equal to PR assumed. If not, then I have again to repeat, but I can start with the PR, it will be P calculated. Okay, I repeat again until the two of them are exactly the same. So I have some iterative procedure, and it's because it's an implicit equation. Okay? If you have any doubts how this equation was derived, you can, I think I can put the link here if you want to know exactly what assumptions were made. You can go to that link. Okay, that's a lecture by Curtis Whitson. Wait. Now the back pressure equation. So if you see that, really it's a bit similar to what we are showing here. Okay, that you need. So you need the volume. Okay, that we are giving. That's the G. The volume is this, like what we provide in the reservoir simulator. We have certain Z, okay, we have certain Y, and we have certain X, okay, and that gives you in a way the G, how much do you have in that container. But then on the side of the well, this C and N are capturing all of these parameters. They are capturing the permeability, they are capturing the fluid properties, they are capturing the saturation. Okay, all of that is introduced somehow into this CNN. And those of you who took the course of Harald Aschheim, you know how to calculate. From all of these properties, you know how to estimate CNN. Yep. Who took the course of Harald? Production wells. So you are familiar with what I'm talking about? Yeah? No? Maybe, maybe not. Well, we are going to have a separate discussion on IPR, okay, if you need. If you feel like you need, but at this point you just say, that's a curve. For a given reservoir pressure, I apply certain pressure in the sand phase, and I will obtain certain rate. And if you plot that, it will give you that descending behavior. And when you reduce reservoir pressure, it's just going to be scaled down and down and down. But this CR has information about permeability, has information about properties. What else do we have here? Permeability, properties, saturation. But in this case, it's dry gas, so saturation doesn't change. If saturation doesn't change, the permeability doesn't change. Okay, remember that you have something called, that I hope you saw, this one. Okay, this curve, relative permeability curve, for example, of gas and water or oil. Okay, and that depends on the saturation of gas. Yes, but in this case, we are all the time in the same saturation. We have no condensation of liquids in the reservoir. Yeah, you have seen that curve before. Yes, okay. So we have that equation, and we have this equation. How do we use this equation? So we have to provide the C and the N. We have to provide the reservoir pressure, and then we have to provide this bottom hole pressure. And then we can calculate how much we are producing. Clear? Okay, let's go to the exercise. The exercise is on my website, folk.ntnew.no, Stanco, courses, class files, and today's date. Okay, I hope that all of you have downloaded. Maybe I will put the link here. Okay, and let's start with the example. So let's see what is provided. I need G, the initial gas in place. That's nice. I need that for the material balance. The reservoir temperature, I need that to calculate the Z, the deviation factor. That's fine. The PI, I need also on the material balance equation. Here you see you have the C and N that somebody estimated for us. You went to the petrophysicist, they got the properties, you went to the production engineer, and they say, okay, for that particular well of that particular size that you're thinking, that might be a C and N that represents the productivity of the well. Okay, so here we have a bunch of steps that are mixed. Okay, and I hope to have a separate discussion on IPR a bit later. Then you have the gravity. What do you need the gravity for? The specific gravity of the gas? For the critical properties T and C. And we have how many wells we're going to use for that development. Okay, this IPR, if you remember, that's only for one well. And usually a field, we don't develop it with one well. Okay, we need a bunch of them. So initially I'm assuming 4. And that's a bit similar to what the input I use in the reservoir simulator. Okay, but then what else do I need? I think I mentioned, right? You need, for each well, you need a minimum flowing bottom hole pressure, and you need a rate. Okay? So which minimum flowing bottom hole pressure should we use? We are going to talk about facilities later, okay? But we assume that our system is going to look something like this. Okay? You have the reservoir, and it goes all the way to some facilities. And these facilities we're going to talk later, but that might be, usually they are between 50 bar and 30 bar. So you know the pressure at least has to be that number. And when I go further and further and further, the pressure of course is going to increase to be able to flow that fluid through the system. So for that, that's a value that initially people take it from the top of their head, or they maybe talk to some production engineer to say, what do you estimate if we think that this offshore structure will be, for example, 10 kilometers away? Okay, so what do you think will be the pressure drop? And the production engineer really doesn't know, goes to bed, sleeps, thinks, and then asks his wife, please tell me a number, and then a number greater than 50, and that's what he comes back with. The reservoir engineer say, use this number. Okay, roughly, but not exactly like that. So we know it has to be greater than 50. So what do you think if we assume 120, for example?
It's okay.
It's okay? Accepted? Yeah? We say 120, and we need more or less 70 bar pressure drop through the system. Okay, it's gas. Okay, so let's assume 120. And then we have how much we want to produce And in this case, I'm going to say every well is identical, so it's the same if I provide the rate of each well or if I provide the rate of the field, because each well is identical. Yes? And I say I want to produce from this field 20 million. Okay, has the discussion we had before. Usually these fields, if they are standalone, I have to make their own facilities. I have to produce them in plateau mode first and then decline. And if you remember the rule, what was the rule? I have to offtake, the annual offtake for a gas field. How much is it? If you remember that number, it was something like 3% per year. You remember that? Long time ago. Yeah, 3, between 2 and 3%. Okay, so annual offtake for gas is the between 2 and 3% of the initial gas in place, okay, of G. And if you do that calculation, you will obtain roughly 20 million. We're not going to spend time, but you will obtain roughly a number close to 20. But I told you gas depends on the contract, on the where are you selling the gas, who are you selling the gas, if they need certain gas for some amount of time. So really it has more variation, but that's where roughly the number came from. Okay, so now let's go time by time. Okay, now let's go at one particular, so that's exactly what the reservoir simulator is doing. It's going time by time by time, doing calculations in a gradual way. So the first thing we're going to make, here you see to the further right, the reservoir pressure. That's going to be just initial reservoir pressure, okay, 276 bar. And we don't want all of these decimal points, so we take them away, just one. Then with reservoir pressure, I can calculate the initial compressibility factor, and that will be, okay, so for that we go to our BBA module. That's not how you go to the BBA module. Okay, and if you see on the modules, you have one module called C factor, set factor. And in that module is saying, please give me the pressure, the temperature, the specific gravity of the gas, and tell me which units you're giving me the pressure and temperature. And in our case, we're going to use unit number 2. Unit number 2 is metric, and the pressure is in bar and in degrees Celsius. So we're going to here provide the current reservoir pressure, the current reservoir temperature, and the specific gravity of the gas, and the 2. Okay, so I'm going to make that very quickly. So that's, to access it, you either type it, cfact, standing, and then if you want to see the input, you don't remember, you put fx, and you say pressure, temperature. Remember the temperature, I block it, because when I go down, I don't want it to be dragged. Then the specific gravity of the gas, okay, I also block it, and the unit is going to be 2. And I obtain a set very close to 1. That means almost ideal gas. Okay, how much I have produced, I'm now initially at the beginning of the production. How much I have produced at that point in time? 0, okay? I haven't produced anything. So that will be 0. Delta GP is how much I produce in the year. Okay, here the year, it says the end of year 0. Okay, so let me make that comment here. That year indicates the end of the year. So the end of the year 0 is exactly when I am supposed to start producing. I'm supposed to start production. The end of the year 1, I have been producing some amount for that particular year. Okay, so I haven't produced anything. So delta GP is how much I have produced in the year. I haven't produced anything in year 0. I'm just starting. And also delta GP is 0. GP, sorry, the cumulative production. And the recovery factor is GP over G. Yes, that's something I need for my material balance. I need 0, of course. No big science, rocket science in that part. But now I want to calculate how much my well can produce. And for that, reservoir simulator does it, and just pay attention to this part, in the following way. Reservoir simulator says, you gave me two values, the value that you want and the minimum value that you require to flow, the minimum. So what I'm going to do first, I'm going to put the pressure on that equation that you gave me, the minimum pressure that you need on this equation, and I'm going to calculate what is the maximum that you can produce. And that maximum, I will call it the potential flow. Now, what happens if the potential is greater than what you want to produce? Can you produce what you want to produce or not? You can produce it, right? Because you could produce, if you put the minimum pressure that you want, you can produce more. So you can regulate the pressure, put it higher and higher and higher until you produce exactly what you want to produce. Yes? But what happens if the potential is lower than what you want to produce? Then you cannot, right? So let's make that just note here on the. So first I calculate the well potential. Reservoir simulator is calculating well potential by applying the provided PWF mean in the sand phase. Okay, I call it the sand phase. If we see, for example, the completion of a well, here I have a reservoir, and here I have my tubing and my production packer. So it's the pressure that I'm applying just in front of the sand. I call it the sand phase, just in front of the reservoir. So I first apply that, okay, PWF mean, and what I will obtain from the IPR equation, QG CR PR for that particular time, squared minus PWF mean squared, and that Q will be QG potential, the Q that I could potentially produce, the maximum rate that the well can produce. So if QG potential is greater than QG target, okay, remember that each well also has a target, then I can produce the target rate, right? The only thing is I have to increase the pressure, but the pressure will still be higher than what I need to flow from that point to the rest of the system. Okay, the target rate provided is feasible. Okay, and I'm happy. On the other hand, if the QG potential is less than the QG target, that means I cannot produce the target rate provided, right? Then in that case, I have no choice, but I have to start producing just the potential. You say, okay, I cannot fulfill that rate that you gave me, but I will try to produce as much as possible, and this is the most that I can give you. Okay, that QG potential. That clear? Yeah. So usually in the simulator, initially you have a lot of energy. So you can produce, the potential is all the time greater than the target. But with time, there comes a point where it becomes less than the target, and then the simulator changes from operating in constant rate to operating with constant bottom hole pressure. Okay, and we are going to make that example in Excel. Okay, so let's calculate that Q well potential. Okay, so for that I think we can check the formula that we have, and it's called in flow equations IPR-QG. Okay, to give me the IPR of the gas, and it has to give me the rate of gas with back pressure coefficient, back pressure exponent, reservoir pressure, and flowing bottom hole pressure. So that's the equation I'm going to use. I can call it IPR-QG. I want to use this not to make any mistakes. Then I say the back pressure coefficient, I'm not sure where it came from, God gave it to me and I just accepted. And I also block it. Then PR, the current PR, and that's going to change when I drag it down. And the bottom hole pressure that I'm going to use is the minimum bottom hole pressure. That's what the reservoir simulator is doing, okay? You are doing exactly the same that it's doing. So I obtain 6, that's a huge number, okay? 61 million standard cubic meter per day. And the field potential, if I have 4 wells, it will be just 4 times that number, right? This number times 4, and I block the 4, and I get 247. Yes? So now the simulator comes and makes the check. The simulator says, that's how much you want to produce, and that's how much you want the field, the target. So I can produce the target, so I say the Q of the field is just equal to the target. Okay? I don't want to produce the maximum that you can produce, I want to produce less. And I'm sure there will be a pressure that will give me exactly that rate. Okay, and actually the simulator calculates that pressure. So that's one question. How do we calculate that pressure? Because remember, we mentioned before that the simulator is giving both, if you remember that small discussion, is providing rate. In that case, it's going to provide just the plateau rate for that time, but it's also giving me bottom hole pressure. Okay? For that, I just go back to my formula, my IPR, but now the rate will be the target rate, C and N I have them, PR I have it, and from there I clear PWF. The operating PWF for that to get exactly that rate. So let's make one more column that I forgot to include and say PWF, and that will not be bin, but that's actually the one that we are operating at. And I will use the IPR formula, but now in that case clearing the bottom hole pressure. And here I need again the C exponent, the N exponent, the reservoir pressure, and the Q I need that number, right, divided by the number of wells. Yes, because it has to be the rate per well, the plateau rate per well. Okay, that we are going to change the format. Let's change it to number. Okay, that tells me I have to apply 267 in the sand phase exactly to get the plateau rate. Right? Now let's go to the next year. Now let's assume what the reservoir simulator is doing. It's assuming that for a short period of time, the rate will remain constant. Okay, from year, let's say now we are taking a big step, okay, a huge step. But now let's assume from the end of year 0 to the end of year 1, you are producing in a constant way the plateau rate. Yes? So from there we can calculate delta GP. Delta GP will be the rate, this rate, right? This rate times, remember, to calculate the reservoir pressure, you need the rate of everything that is draining out of the same container. And all of that is all wells, okay? Is the rate of the field. Times, I will make it general, so I will say times this year minus this year, okay? And is that all? Think about the units. Do the units match? Huh? Yes? Yeah, let's see. This number is in standard cubic meter per day. This number? Years. So I have to have the number of days per year, right? To make it consistent. So how many years are we producing usually? How many days in a year?
65.
Okay, that's not exactly true because we all the time have some stops due to maintenance, due to we have to do any operation in the well, due to testing. So we're not producing really the 365 days. But let's put 365. But usually they have the companies have something called an uptime factor, okay? And they say we have an uptime factor of 90%. That means that they're able to operate 90% of all the days in the year. 80%, 95%, etc. So we can say 365 with, let's say, 90% uptime. Yes? Now that's what I have produced in that year, and the GP will be what I produced from before plus what I'm produced now. Yes? Now, let's see. Now I can also calculate the recovery factor. That is going to be a very small value, 0.02, 0.2%, which makes sense. Okay. Now so here I have this iterative process that I told you. That we need assume a pressure, get set, then calculate set, again use the pressure. What I'm going to make your life easy, I'm going to say the pressure change is not going to be much, I assume, from year to year. So the set shouldn't change much from year to year. So what I'm going to use for that set, I will use the pressure from the previous year to avoid this implicit calculation. The implicit calculation, probably you're going to get it in the exercise. Okay? But here in class, I'm going to say, I take the pressure from the previous to calculate this current pressure. So let's make that C factor standing. Pressure, I use the pressure from the previous. The temperature, I have to block it. Then specific gravity, again I have to block it. And the unit, if you remember, is 2 because we are working in metric. And then here I have a, so let me copy that, not good. And now I want to calculate reservoir pressure using the material balance equation that I call MB, M balance tank, PR. And here I have to provide the initial reservoir pressure is just that number, and I block it. Initial deviation factor is just that number, and I block it. Current set, that is going to use all the time the pressure from the previous year, and the recovery factor. Okay, and I got that the pressure truly didn't change that much. Okay, 269. But if you want to make it better, now you should use 269 set. You obtain a different pressure, repeat and repeat and repeat until that value reach some convergence. Okay, now we repeat exactly the same. One question, can I drag here down all of that? Yes or no? Well, these two I can drag, right? So I can apply the same. Now I'm applying, if you remember, minimum flowing bottom hole pressure. I'm getting the potential of the field, and that value has to be greater than 20. It's greater, so I can still produce 20. Yep. Okay, that value I'm going to, let's make here a flag, okay? I want all the time that that number will be greater than this number. Yes? So let's make here the Q of the field is if this number is greater than or equal than this number, and I'm going to block it. That's how much I desire from the field, how much I want to produce from the field, then you should use that value. It doesn't want. You're going to use that value for the rate. But if not, you're going to use the potential. You're going to produce the potential, right? And here it gave me 20. I drag it down, gave me 20 again, and 260. So now the nice thing about Excel is that I can just drag it down, and it will repeat the same calculation with every year. Okay? So everything more or less under control. Okay, you see 20, in all of them, the potential is greater than the rate. Okay, potential is greater than what I want. Potential is greater than I want. But there will come a point where the potential is actually less than what we want. In that case, I will start producing I will change from constant rate to constant bottom hole pressure. Yes? All the way until, okay, and if you see the pressure, it's all the time going to be in 120. So now when do I stop the calculations? Do I continue all the way until infinity? Okay, because it can go all the way. Yeah, here we have what happened here. Reservoir pressure is doing something strange. Okay, so why it reached 120 and it stayed there? That's something that is not correct. Okay, what is happening here? What happens when reservoir pressure reaches this minimum bottom hole pressure?
No flow.
I won't have any more flow. So all the results from this point down, they make no sense. Okay, because I'm applying. Actually, I'm not sure what happened here. Why it should be changing, right? Because we are still producing from the same. Yeah, maybe there are some decimals. It's changing very, very slightly. Okay, it hasn't reached yet 120. So you all the time get a bit more flow, a bit more. Till eventually I won't produce. So let's plot, now in these 3 minutes that we have, let's plot what will be the production that I predicted from the field. Come a bunch of things that I don't want. That's called the production profile. And that really is the first input that we have to use for our economical, for the calculation of the NPV. And if you use reservoir simulator, not taking anything into account, you saw all the information that you have to use, and you have to assume a minimum bottom hole pressure. You can change, nothing is prohibiting you from using one for each year, okay? But you have to give the simulator a value, and that value is an estimate. Okay, for early phase, really you don't know, you ask the production engineer, and the production engineer doesn't have really any information, so they just make an assumption. They say 70 bar, we estimate more or less for the length, We assume certain pipe. So let's say 71. But you will see what we are going to do on Thursday. We're going to see now to include the rest of the system and see how that affects our calculation. So let's make it a bit nicer. Okay, and usually I don't continue, like I told you, you don't continue all the way until reservoir pressure is the same as the minimum. But you usually use a cutoff value. That's the minimum economical rate that I can get from the field. Okay, for oil is someplace between 5,000 barrels and 3,000 barrels. For gas, I'm not sure, but you have a cutoff. We can, let me take that. Is when the revenue cannot pay anymore for the expenses. Usually that's when you try to. That's the minimum rate. Okay, so here I define a cutoff, or is the minimum economical field rate. Okay, for example here, and then you don't do any more simulations after that point. If after that the model is giving less and less, I just stop the simulation at that point. Yes? Any question? As I told you, it's a shame we cannot use reservoir simulator. It's really very interesting. You need to put all the input. You need to gather and quality control all the input. But this is, in a simplified way, how the simulator is working. Applying the pressure, calculating a potential, and then comparing the potential with what you provided. And making, if you see here, we are assuming, if you see, for example, how are we calculating the GP? Okay, GP, we're saying that the rate is constant for that particular year. Yes, the rate is constant for that particular year. But in this case, you're assuming that that rate is constant for that year. Yes, but it really changed quite dramatically. It changed from 20 all the way to 16. So it was a variation of maybe 25% of the rate. So assuming that is constant is not really a good assumption. So you can have more complicated methods to calculate GP, and that, if you remember the trapezoidal rule, that we say that the delta GP is equal to, anybody remembers, time I plus 1 minus time I times QI plus 1 plus QI divided by 2. If you refresh your numerical methods, but I can make it actually like a trapezoid, and then I can improve much better the calculation of the GP. That clear? Yes? Any questions? Comments? You want to run out of here? You have another class? Okay, so please try to, sleep on it, and we come. Then on Thursday we're going to see what is the influence of the rest of the system that we are neglecting. And for that we have to talk about flow equilibrium. So see you next Thursday.